Morning to all of you. In today's session, we will be looking at analog to digital conversion process, as well as we will be looking at digital to analog conversion. Okay. So in previous sessions, we have already discussed about what is digital signal processing, what is signal. We've seen some of the examples of signals which are dependent on some independent variables, as well as we have seen some basic elements of digital signal processing system, as well as we have seen some advantages as well as drawbacks of digital signal processing as well as analog signal processing. Right? So today we'll be looking at analog to digital conversion. So in analog to digital conversion process, there are three basic steps. Okay, first one is called as sampling, which is performed by a device which is called as sampler. Second step is called as quantization, which is performed by the device which is called as quantizer. And third step is nothing but coding, and this is performed by a device which is called as a coder. Okay. So as we have seen, most of the signals such as speech, biological, radar, seismic, sonar, and various communication signals such as audio and video signals are analog in nature. So to process this signal by using digital signal processing system, we need to convert these analog signals into digital form. So therefore, we'll be using this analog to digital conversion process. Okay, which involves these three steps. Okay, that is sampling, quantization, and coding, performed by the devices sampler, quantizer, and coder respectively. So let's look at how these steps will be performed by the analog to digital converter, which is the device for converting analog signal into digital signal. So your analog signal is generally represented as XA of T. So this XA is nothing but the analog signal, and which depends on the independent variable small t. So this analog signal will be given as an input to the sampler. So this sampler will take analog signal as an input. Okay. After that, this XA of t will be converted into the sample signal, which is represented as x of n, which is nothing but x of nt, small n, capital T. So this small t in analog signal is simply replaced by the value small n, capital T, to get the sample version of the analog signal. Okay. So this is your sample signal, which is also called as discrete and signal. Okay, but it is continuous in value or amplitude. So it is continuous valued signal. Right? So the output of sampler is referred as or denoted as x of n, which is nothing but the modification of analog signal where the variable independent variable small t is replaced with value n into capital T. Okay, so this signal will be applied to the next device, that is nothing but the quantizer, which performs the quantization process. And the output of this quantizer is denoted as SQ of n. So this is called as what? Quantized signal. This signal is discrete time as well as discrete valued signal. Okay. So when you are quantizing the sampled values by using quantizer, we are quantizing these sample signal using quantizer, then there will be the difference between quantized signal and the sample signal. This difference is called as quantization error. Okay, we'll be going into details of all these things in next lectures or sessions. So after this quantized signal will be given to the next block, that is nothing but the coder, which performs the coding operation and converts your quantized signal into actual binary codes. Okay. Depending on what type of coding you are using here, it will be converted into these binary codes. This is nothing but your digital signal. Okay. So the output of coder is actual digital signal. Right. So this complete diagram can be referred as what? Analog to digital converter. This comprises three different steps, that is sampling, quantization, coding, performed by the devices, that is nothing but sampler, quantizer, coder. Sampler will take input signal, that is nothing but the analog signal. So the signal is continuous in time as well as continuous in value. Continuous value signal. Okay, so sampler will convert this continuous time, continuous value signal into discrete time, discrete value signal. Okay. And then this sampled signal will be passed to the quantizer, which converts the given signal into discrete time, discrete valued signal, which is also referred as the quantized signal. This quantized signal will be given to the coder, which converts that quantized signal into actual digital signal. Okay. But in our subject, that is digital signal processing, or whenever you are processing any analog signal in by using digital signal processing system, maybe hardware, that is digital hardware, or if you are using some software to process that signal in digital form, so we'll be using the sampled version of the analog signal. Okay, so in this subject, that is throughout digital signal processing subject, we will be using this x of n for computation purpose. Okay, so whatever operations we will be performing on the sampled version of the analog signal instead of the quantized signal or the digital signal. The reason for that we'll be looking in next lectures. Okay, next sessions. So to summarize, we have seen, so in this case we have seen the three steps, that is nothing but sampling. Okay, so in this case an analog signal, so if I want to represent an analog signal, just for example, if I am considering this analog signal, okay, which is continuous in time and continuous in value or amplitude, right? So I will refer this as what? Analog signal which is continuous time and continuous valued signal. Okay. So this will be given to sampler. Okay. So this signal, instead of calling it as x of x amplitude, I will say it as x of t. Okay, that is analog signal. So this analog signal will be given to the sampler. Okay. So this will be an input signal given to the sampler. So the output of sampler can be denoted as x of n, which is nothing but say of small n capital T. Right? X of small n capital T. So this signal is called as what? Sampled signal, which is discrete in time but continuous in value. Okay. So how this signal will be represented? Okay. So in most of the books, the wrong representation of this sampled signal has been given, as well as you will find in so basically this sample signal is represented like this in most of the books. Okay. But actually, if I want to map this analog signal as the sampled version of the signal, okay, so then how it will be represented, the output of the sampler. Okay, so here the signal will be represented like this. Okay. Like this it will be represented. So these are the samples. Okay. These are nothing but the samples which are occurring after every capital T intervals. Okay, so if I'm starting from 0, so it will be 1, maybe you can add as 1 capital T, so it will be twice T, is thrice T, likewise total capital NT. Okay, time period. So after every capital T time interval, uh, instead of calling it as directly T, here after every capital T interval these samples are occurring. Okay, so capital T twice T likewise. Okay. So there is what some interval between occurrence of each amplitude value. Okay, so between these two sample some interval will be there, so same interval will be here between these two samples, same interval will be here, right? So that means time is discrete in this case. Okay, so therefore we are calling it as what? A discrete time signal, right? So this sampled signal is nothing but the discrete time signal, because time is discrete, it is not continuously varying. For some time period samples are not there, okay, or values are not there, right? So therefore we are calling it as a discrete time signal. But if you observe the amplitude or values, so it is varying continuously here. Okay, so it is varying continuously, right? It is not any fixed value here, it is variable var. Okay, so it is varying continuously. So therefore, we are calling it as what? Continuous valued signal, but discrete in time. Okay. So likewise, these samples will be there. So this sampled version of signal will be represented like this. Okay. So here these samples are occurring after every capital T period. Instead of representing capital T twice T here, I will represent it after every sample, that is capital T twice T, then 3T, 4T, 5T, and so on up to capital NT. Okay. So this is nothing but your discrete time signal, that is sample signal. Now this sample signal, so if I am considering some value here, just for example, these values are present from 0 to, just for example, 5, okay, and minus 5 here. Okay. So in this case, I can consider that for every time period value is present there, as well as time is continuously varying, as well as value is continuously varying. Okay, so therefore I am calling it as what? Continuous time, continuous valued signal. That is nothing but the analog signal. Okay, but in this case time is discrete. Okay, time is not continuously varying. Okay, it is taken after every capital T interval. Okay, time interval. Right. Here this small t is nothing but the time unit for analog signal. Okay, capital T is nothing but the sampling interval. Right. After every capital T time interval, sample will occur. Right. So therefore it is called as what? Sampling time interval. Right. So your sampler is converting this continuous time and continuous valued signal into discrete time but continuous valued signal. So if I'm considering this first sample, okay, here this is the first sample. So for this sample the value may be from, okay, the highest value I have taken here as 5, just for example. So this value is varying from maybe 0 to 1.2, right? Just for example, the highest value here is 1.2. Here it may be 1.4 to maybe 1.8. Okay, likewise. So that means multiple values are present between this time interval in that sample. Okay, so therefore it is continuous valued, but it is discrete in time. Okay, so this signal, that is sampled signal, will be given as an input to the quantizer. Okay, for performing the quantization operation on the sampled signal. So how this output will be represented? So again, this quantized signal is represented or denoted by SQ of n. Okay, the output of quantizer is nothing but the quantized signal, which is discrete in time as well as discrete in value. Okay, so it is discrete time, discrete valued signal. So if I want to represent the quantized signal, how it will be represented, right? So here the amplitude was continuously varying, right? But now time as well as amplitude will be discrete. So that means a fixed level will be assigned, which is called as what? Quantization level. A fixed level will be assigned to each sample, okay, in quantized version of the signal. So it will not be continuously varying. Okay, it has some fixed value. Initially this first sample was varying from, here I have said that it was varying from 1.2 to maybe 1.4, right? So or maybe here it was varying from, first sample was varying from 0 to 1.2, right? So I consider it as it is varying from 0 to 1.2, but now I have fixed it to, just for example, I have fixed it to 1. Okay, simply 1 instead of 1.2 or 1.1. I have fixed it at 1. Second sample was varying from maybe 1.4 to 1.8, so I will fix it to, just for example, 1.5, right? Similarly, all these samples now have some fixed value here. Okay, so that means here I can consider it as 4 is the value. Similarly, again 5 I have taken, just for example. So likewise a fixed value will be assigned. So here uh, time is discrete as well as value is discrete. Okay, instead of initially it was varying like this. Okay, it was varying like this, it was continuously varying, but now there is a fixed value assigned to this sample. Okay, so therefore it is discrete in value as well as it is discrete in time. Okay, so that likewise this output will be represented. So here again, just for example, this value was continuously varying. Okay, here just for example, this value is varying from minus 1.3 to maybe I can take it as 1 minus 1.4. Okay, so again I will assign the sample as a fixed value. Maybe here I can assign 1 minus 1. Okay, so likewise for all these samples some fixed quantization values, which are also called as quantization levels, okay, will be assigned. Just for example, here I am assigning it as minus 1.5. So likewise this quantization process will be carried out. So here initially our signal was what, continuous in value as well as continuous in time. Here it was discrete in time but continuous in value, right? So it was discrete time, continuous valued signal, but now here it is discrete time as well as discrete valued signal. Okay, so discrete time as well as discrete value signal. So this is called as quantization process of the quantized signal, right? Output of the quantized. So depending on the number of quantization levels that you have taken. Okay, so just for example, if I have taken here uh, quantization levels from 5 minus 5 to 5, right? Initially there may be all values present here from minus 5 to 5. It may be 1.25, it may be 1.34, likewise. Okay, but here I have restricted those values, number of values in the actual quantized signal from minus 5 to 5 with maybe zero point 0.5 difference in each value. Okay, so that means minus 5 then minus 4.5, right? So likewise minus 5, minus 4.5, minus 4, minus 3.5, minus 3, right? Minus 2.5, minus 2, 0 will be there, right? Before that minus 1.5, minus 1 will be there. Again then 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5 and 5. Okay, so total how many values will be there? So it will be 9 plus 9, 18 plus 1, so total 19 values will be there, right? So if I'm considering total 19 quantization levels, okay, in my quantized signal, so to represent this quantized value, basically this quantized signal will be given as an input to the coder to convert it into actual digital signal. Okay, so the output of this coder is nothing but the digital signal, right? But how these values will be coded. Okay, so these values will be coded by using, maybe you can use binary coding or any other coding. So if I am using binary coding, so and considering total 19 tables, okay, in quantized signal, so to represent 19 values, okay, how many uh, bits will be required in my binary code. Okay, so for that purpose, just for example, to represent 19 values, I have to use 5-bit combination. Okay, because if I'm using 4-bit combinations, it will be 2 raised to power 4, that is 16. So only 16 values I can represent. Okay, so instead of using 4-bit representation, I will use 5-bit representation. So which gives me total 32 values, but out of this 32, only 19 will be utilized and the remaining values will be unused, right? So I can code it as how I can code it. So minus 5 may be represented as 5 times 0, right? Then minus 4.5 I can represent as 4 times 0, 1. Then minus 4 can be represented as 00010. Then minus 3.5 can be represented as 00011, and so on. Okay, so your last value, like this, will be uh, value 5, right? So which can be represented as using the code for the value 18. Okay, so how it will be represented? So it will be simply represented as so 1 0 0 1 0. Okay, that is 16 plus 2. Okay, that is 18. So total 19 values are there. Okay, starting from 0. Okay, 0 to 18, total 19 values are represented. So starting from minus 5, so minus 5 I can represent it as binary code 5 times 0, right? Minus 4.5 I can represent it as 4 times 0, 1. So it depends which type of coding you are using. So here if I am using binary coding and starting values from minus 5 to 5, then I can use sequentially, I can use the representation of 0 using 5-bit code, okay, as the value of minus 5. So this is the complete what analog to digital conversion process, in which initially your continuous time continuous value signal will be converted into discrete time continuous value signal by using sampling process or sampler. Then that discrete time continuous value signal is converted into discrete time discrete value signal by using quantizer. Then the discrete time discrete value signal will be given as an input to the coder to convert it into actual digital signal. But in digital signal processing, we will be using this x of n. Okay, that is nothing but the x of n, that is nothing but the sampled version of the signal for processing purpose. Okay, the reason for this, because this sampled version x of n should be used for signal processing operations, because when you are applying quantization process, so there is some signal loss. Okay, because you are fixing some values here, right? Just for example, this sample will be fixed like this. Okay, this will be fixed like this will be fixed like this. So there will be difference between this x of n and xq of n, which is called as quantization error. And most of the time this quantization error is hard to eliminate. So therefore, instead of considering quantized value for processing purpose, we'll be using sampled values, okay, for digital signal processing. Okay, so in this subject or throughout this subject will be performing different operation on this discrete time signal. So uh, will be only considering this x of n, that is the sampled version of the analog signal for digital signal processing. Okay, so everywhere you will find the word discrete time signal throughout the digital signal processing subject. Okay, so you are referring to x of n when you are calling it as a discrete time signal. It is not the actual digital signal. Okay, so in this digital to analog conversion process, okay, these digital to analog converters, okay, which comprises three different blocks, that is sampler, quantizer and coder, are of various forms. Okay, so these digital to analog converters can be designed as zero order hold or a staircase approximation, or maybe you can design it as other approximations such as linearly connecting a pair of successive samples, which is also called as linear interpolation, or fitting a quadratic through three successive samples, which is called as quadratic interpolation. So by using these different methodologies, we can design these digital to analog converters. Okay. And while converting or getting analog signal back from the digital signal, that is in case of digital to analog conversion process, we are seeing this analog to digital conversion process, but in case of digital to analog signal conversion process, initially your analog signal should be properly sampled. Okay, so sampling rate plays an important role. Okay, whatever these uh, values are here, that is nothing but small t, this is nothing but the time unit for your analog signal. Capital T, which is also called as sampling interval. Small n is the time unit for the sampled signal or discrete time signal. Okay, but here we have taken the sampling interval as what? Sampling time interval as capital T. So selection of this capital T, which is called as sampling time interval, plays an important role when you are trying to convert your analog signal from the digital signal. So analog signal can be reconstructed from the samples, provided that the sampling rate is sufficiently high. Okay, but on other hand, quantization is irreversible process. Why it is irreversible? I just said that there is some signal loss. Okay, we are seen here when you are using some of the techniques here, okay, to fix this value. Instead of representing it as continuous value, we are using a fixed value here, so there will be some signal loss. So because of that, this quantization process is irreversible, so which result in the signal distortion. So amount of distortion is dependent on accuracy as measured by the number of bits in analog to digital conversion process, right? And the cost may increase with an increase in accuracy, or with an increase in the selected sampling rate. So if you want to design the analog to digital conversions having higher sampling rate, so it cost will be more. Okay, so for this session, we need to keep in mind these three steps in analog to digital conversion process, that is nothing but sampling, quantization and coding. We have also seen a representation of what will be the input to the sampler. Okay, that is nothing but continuous time continuous value signal. The output of sampler is the sample signal, which is discrete time but continuous value signal, which will be given to the quantizer. The quantizer output is called as quantized signal, which is discrete time and discrete value signal, which will be given to the coder, which converts it into actual binary code, that is nothing but the digital signal. Okay. So in next session we'll be looking at uh, how sampling of an analog signal can be performed, and as well as we'll be looking uh, sampling theorem. Okay, so those topic will be discussing in next session. So thank you for joining today's session.